Hello everybody and welcome back to another Algebra 1 video. Today we'll be continuing with lesson 5.5 on comparing linear and nonlinear functions. The graph of a linear function is going to show a constant rate of change in both its x and y values, whereas a nonlinear function will not have a constant rate of change in both the x and y, just meaning that its graph is not a line. And so when they say rate of change, they just mean to say that you're adding the same amount between each interval in your x and y values. And so in this example here, they're going to typically give you a table of values with your x and y values organized, and they're going to ask whether it represents a linear or nonlinear function. And so all you have to do is find that the rate of change is constant. And so from 3 to 6 for your x values, you're adding 3. From 6 to 9, you're also adding 3. And from 9 to 12, you're adding 3 once again. So you see here among your x values, you're adding the same amount, 3, to each of your x values. And so that means that your rate of change stays constant in your x's. Now, although the rate of change stays constant in your x values, you do have to make sure that it will stay constant in the y's. So looking at our y values right here, we're going from 40 to 32, so that is a rate of change of minus 8. From 32 to 24, you're subtracting 8 again. And from 24 to 16, you're subtracting 8 once more. So you see here that your rate of change, once again, is constant in your y values. And this time, you're just subtracting 8. And so as x increases by 3, y is decreasing by 8, the rate of change is constant, and so your function is going to be linear. Let's look at another table here. We're going to tell whether it represents a linear or nonlinear function. First, I'm going to take a look at my x values. I have 1, 3, 5, and 7. From 1 to 3, I have a rate of change of 2. 3 to 5, I'm adding 2 again. And from 5 to 7, you're adding 2 once more. So you see the rate of change is constant in your x values. As for your y values, however, from 2 to 11, you're adding 9. But you see here you have a big jump. You're going from 11 to 33. So now you're adding 22. And then another big jump from 33 to 88, you're adding 55. And so if you look at your y values, the rate of change is no longer constant. You're no longer adding or subtracting the same amount between each y value. And although it might be constant in your x's, it needs to be constant in both your x and y's. And so as x increases by 2, y increases by different amounts. The rate of change is not constant, and so the function is not going to be linear. Here are a few more examples for you to try. This first table, we have x values 0, 7, 14, and 21. So let's find the rate of change of our x's first. So from 0 to 7, we're adding 7. From 7 to 14, we're adding 7 again. And from 14 to 21, we're adding 7 once more. So far, our x values are constant, and this is so far representing a linear function. But we have to confirm that the same is happening in our y values. So from 25 to 20, you're subtracting 5. From 20 to 15, you're also subtracting 5. And from 15 to 10, you're subtracting 5 once more. So you see here you also have a constant rate of change in your y values. So as x increases by 7, your y values are constantly increasing by 5 also. Your rate of change is constant, so you know that this function is linear. As for this second example, we have our x values 2, 4, 6, and 8. So from 2 to 4, you're adding 2. From 4 to 6, you're also adding 2. And from 6 to 8, you're adding 2 once more. And so your rate of change in your x values are looking good. They're all constant. As for your y's, you have 8, 4, 0, and negative 4. From 8 to 4, you're subtracting 4. From 4 to 0, you're subtracting 4 again. And from 0 to negative 4, you're subtracting 4 once more. Again, your y values are constant, as are your x's. So as long as your rate of change is constant, your function is going to be linear. Now we're going to be given an actual graph and see whether the function represents a linear or nonlinear function, then explain. This one is actually pretty simple. You just have to see if the graph is a straight line or not. In this case, we see that this function is not a line. It actually has two curves right here, so the function is going to be classified as nonlinear. Now for this graph, we see that it is a horizontal line, and since it is a line, it is a straight line, we know that this graph is going to be linear. For this next example, we actually have one of our special functions, which was an absolute value function. And so looking at this, you might feel a little bit torn because you see here that your absolute value function, which if you recall is f of x equals absolute value of x, is formed by two straight lines. However, it's forming this pointed V shape. It's not exactly a straight line. And so would this represent a linear or nonlinear function? Now, actually, a absolute value function can be rewritten as a piecewise function. All of our special functions encompass all the piecewise functions, such as stepwise functions and also absolute value functions. And so f of x equals absolute value of x can actually be written as a piecewise function, f of x equals x if x is greater than or equal to 0, and negative x if x is less than 0. So you might wonder how this might come to be, but actually, these two linear equations represent the two linear equations that are making up our absolute value function right here. So if you have f of x equals x, and you want it where x is greater than or equal to 0, now your y-intercept would be at 0 right here, and your slope would be 1. So you're going to rise 1 unit and run 1 unit to the right, rise 1 unit and run 1 unit to the right, and you see these points are laying on this line, this portion of your absolute value function. And you would have a solid point here where x is greater than or equal to 0. This would be everything from 0 onwards that is above 0 on the x-axis. And as for the other portion, you have negative x if x is less than 0. And so you would have an open circle here, and your x-intercept would still be 0, but this time your slope is negative 1. So rather than rising 1 unit and then running 1 unit to the right, you're going to rise 1 unit and run 1 unit to the left. And you see your points are going to fall on this other line that's creating your absolute value function. And so in the end, this does represent a linear function. It's just made up of more than one linear function. Now you might be given a few equations and be asked to tell whether it represents a linear or nonlinear equation. And so in the case of this problem, we're actually given 4 different equations and we're being asked to tell which one represents a nonlinear function. So if you recall, linear functions are usually expressed in the slope-intercept form, which is y equals mx plus b. And so m is going to represent your slope, and usually you'll have a number that's substituted for m, and then you'll have a constant for your b value that represents your y-intercept. And sometimes you won't see a b value simply because the y-intercept is at 0. And so we're trying to look for y equals to a certain number x plus b. So this is the format we're looking for. And again, it's okay to not have a b value, that just means the y-intercept is at 0. Alternatively, linear functions can also take the form of horizontal or vertical lines, meaning that it's just y equals to a constant value, like y equals to 5, and that would represent a horizontal line, which is still a linear function, or it can be x equals to a constant, like x equals 3, and that would be a vertical line. And again, that's still a linear function. So we're either looking for y equals mx plus b, y equals to a constant, or x equals to a constant for us to know that it is a linear function. And so for a, we see that we have y equals 4.7. Now this is y equaling to a constant, it's 4.7. Now even though it is a decimal value, you're still going to be graphing a horizontal line at 4.7 on the y-axis. So this simply represents a horizontal line, and so this would be a linear function. For letter B, we have y equals pi x. And so you might be looking at this pi symbol and be wondering, well, does that technically count as a slope? Because this is in slope-intercept form. You have the y equals mx plus b. In this case, we don't have a y-intercept. That just means that it's at 0. And so we're wondering if pi can qualify as m. And actually, if you just simplify pi into a decimal, it's just 3.14. So this would be y equals 3.14x, and technically 3.14 is still a slope of a line, and this is in slope-intercept form. So we know that this is a linear equation just with a slope of pi. For letter C, we have y equals 4 over x. Now remember, we're trying to look for equations in the form y equals mx plus b. This is how we're going to know that it is a linear equation. Now m can be a fraction, like 3/4, and this would just mean you're rising 3 units and then running 4 units to the right. However, notice that 3/4 is being multiplied by x. In our equation here, 4 is being divided by x. And we can't actually rewrite this in slope-intercept form. This actually represents another function called a rational function that you'll be learning later on. And so since this doesn't represent a linear equation, we know that this is a nonlinear function. For letter D, we have y equals 4 times x minus 1. Now, I want to see how it would look like once we get rid of our parentheses. So all you have to do is distribute 4 to x minus 1. And that would be y equals 4x minus 4. Remember, you're trying to look for equations in y equals mx plus b form. And this actually matches your slope-intercept form, where 4 is your slope being multiplied by x, and then -4 would be your y-intercept. And so this would be a linear function. Now, does this equation represent a linear or nonlinear function? We have y equals 1 minus x squared. Now, at first you might go, well, maybe you can just rewrite it like this, and it kind of looks like a linear equation in slope-intercept form. You have -1 for your slope and +1 for your y-intercept. However, if you look at your x, it's being squared. If you look at a linear equation, you only have an x, not an x squared. And so this actually represents a quadratic equation. This won't be classified as a linear equation since, once again, your x is squared. And if you were to graph this on a coordinate plane, you'd see that the shape is much different from a line. And you'll be going more into quadratic equations in Chapter 8. For this example, we have y equals 4x over 3. And it might look very similar to our previous example of y equals 4 over x. And remember we said that it wasn't a linear function since you're dividing 4 by x, and so it can't be rewritten in y equals mx plus b form. But notice in this example that x is in your denominator. In this example, x is actually in your numerator, and this can actually represent a linear function. It would just be y equals 4 over 3x plus 0, where 4 over 3 is your slope, so you're going to rise 4 units and run 3 units to the right, and then 0 would be your y-intercept. As long as your x is in the numerator of your fraction, it still represents slope. So this will actually be a linear function with a slope of 4 over 3. That is it for today's lesson. Thank you so much for watching. If you have any questions about any of the examples I do in these videos, feel free to reach out to me at kaelin.david24@gmail.com. I'm always active on my email, so I'll be sure to respond as quickly as I can. For tutoring inquiries, please feel free to reach out to me, again on my email, or one of my collaborators, Joylyn, at 918joylyn@gmail.com. As always, all information regarding lesson requests and additional practice will be linked down below in the description box. Again, thank you so much for watching, and I hope to see you in the next video.